as you will see, this is to do with our initial standpoint that we wanted to have our interfaces such that it's a creation of us, right? We are creating the interface for mapping a shop interface. So there can be much larger than the physical interface that you typically have, right? Typical interface widths that you have in experimental conditions or real materials are of the order of 5 stones. But what I want to use is depending on the microstructure scale that I want to simulate, and that can be, let's say, even to some microns. The question is, because it's a construction I'm doing, are the results that I'm deriving out of my simulations a function of the interface width that I'm choosing? And if they are, that is inconsistent with my initial standpoint that I want to have my simulations independently, right? Because I'm just using it as a construct to map my original problem onto a diffuser. So that construct should be, result should be independent of that. So I must ensure that. All right? So let's see what those, whether that is what that implies. Okay. So what we are going to be discussing now is referred to as chain interface connection. Okay. All right. So let's see what we mean by this. Okay. So all of you have heard about the sharp interface limit. What is this? How many of you have heard about this? Sharp interface limit. None of you have heard? I do not believe that. How many of you are doing PhD? What? Yeah. So have you heard about sharp interface limit? So what is sharp interface limit? Good. So basically you want to derive properties when the interface width, which is the construction, goes to 0, right? And ideally you should be getting to the solution that you desire when you put that value to 0. Because in reality, the sharp interface problem, there is no thickness of the universe. Okay? Now we will see that this is sort of an unrealistic demand from the problem. Because ideally, what you have are finite interfaces which are finitely wide, not vanishingly wide, as you have. They're finitely wide. So what you must be doing, in turn asking the question, can I derive the dynamics I have in the sharp interface space? The problem, not with vanishing interface thicknesses which are too small, you can't use them, right? But with interfaces which are slightly larger and usable. Okay? Nevertheless, because we are doing asymptotics, we will have to discuss this from the standpoint of the sharp interface and then go into it. Alright? So let's start with a simple model because the general characteristics of the equations that we derive are going to be independent. Right? Let's see. So we start with the pure material. you are now conversant with this. Alright, so whatever the equations are, okay, and now first thing is equilibrium. Equilibrium we have all studied right now. It is the case where T becomes 0, so this term drops off, and you are left with these two terms of the equation, which gives you the classical dynamic equation. And we have seen that if you integrate that equation, you essentially recover back the interfacial energy, which is a function of K. Okay? And this equation vanishes when T is uniform, which is other values. Okay? Now, we are going to be asking the precise question is, the question we are asking is, if I undercool my system a little value below Tm, or some value below Tm, right? What is the relation between the temperature at the interface and the velocity of the interface? Okay, what I'm asking is, what is this condition? The relation between delta T and velocity. Okay, so anybody know what this relation is typically in the sharp interface model? For pure mechanics. It's referred to as V by mu, which is the kinetic coefficient, and then this also refers to as the interface kinetic coefficient, which is V. Right? So basically, when the interface is moving with the velocity V, it essentially prescribes that the delta T at the interface must be this value. Okay? This is in the case where, so what is the situation? This is a situation where your interface is rather smooth, right? When your interface is smooth, the atoms from the liquid, when they want to attach onto the solid, they don't have free sides where they can attach. So you must provide an undercooling for them to keep well attached. If it's atomistically rough, typically they have enough sides to go in the interface. And if that is the situation, then the undercooling for that activity is really very small, right? So the two situations are, if you have a smooth interface, that's typically when you have an isotropic faceted interface, you typically have a situation that your interface being smooth, you have some interface kinetics in the problem. That means you need an undercooling at the interface when you are driving the velocity, driving the interface with the given. On the other hand, if you have an atomistically rough interface, right, you essentially have that, you have a vanishingly the kinetic coefficient or the beta that you have in a interface kinetic coefficient is rather small, and the undercooling is rather small. So what you have is a situation that beta tends to 0 for most situations that are relevant to castings under realistic. That means if you do real castings, what are those castings? A simple casting. You put make a sand mold, pour liquid into it. That's a typical casting. right? Or you are doing what is inward casting. All of those castings are typical slow castings in which the conditions are such that you have beta tending to 0, right? Now here then lies the situation, right? Now bear with me with what I'm going to be doing. All agree that when we are over here, when my system is at a, let's say, a steady state condition, what I'm going to have is the solution given by a moving frame, which is this. Okay, we'll have something like this. This is the equation of the motion in a frame that is moving along with the impedance. Okay? Without velocity. Now, as I described yesterday, a typical temperature profile across the interface has a situation that if you are driving into an undercooled liquid, the temperature profile has a form like this, right? Something like this, where you are relatively uniform because you are in a steady state, the temperature is uniform in the solid, and you have the gradient in the liquid. If this interface is rather small, what you have therefore is that the variation of the temperature rather in this interface is really, really small. Okay? So at the leading order, the temperature difference that occurs in this part of the interface, that is inside the interface, the variation is very, very small compared to the macroscopic integer blend that you are having. Okay? In such a situation, the dominating term in the temperature in the interface can be assumed to be some value, which is I'm going to be referring to as T2. Okay? So what am I doing? I'm essentially thinking of making this interface rather small. Think about it. I'm taking from a large interface and I'm reducing the interface small over here. And essentially this temperature drop over here is getting smaller and smaller. And essentially it is going to become a point with the interface width is going down to 0. Right? So essentially, as you reduce down the temperature interface width in the sharp interface case to a 0 value, you essentially reach the limit that the temperature of the interface assumes a constant. Alright? Now if that is the case, then under such a condition, I'm asking the question, what is the steady state revolution equation that I get out of the phi equation? Right? So similarly that I wrote down this, I will write down this as well. Minus V and to make things simpler for us, we'll do things in 1D for all these. So I'm going to write down this as Fs of T naught, which is the interface temperature at in the sharp interface limit. Okay, this is my steady state equation. Alright, this is moving at a velocity v. So this is some temperature T naught, which I'm telling is the interface temperature in the sharp interface. You all know how to integrate this equation now, right? This is something we did yesterday. How do you do it? You basically integrate d phi by dx. And I'm going to be, remember the phi is moving here. This is not a stationary phi. Okay? The phi is moving. The phi of x is moving. And I'm going to be assuming in that limit that the phi evolution that is happening during the motion is very close to the original phase field equilibrium profile moving. Okay, the deviation is small, right? Which is typically true. If it deviates too much, then you are not the original profile, and then your dynamics is typically wrong. So I'm going to be assuming this profile over here is a small perturbation away from what your actual equilibrium profile is. That means when I multiply this with the original profile of equilibrium, I can square this. Okay? So I can do this. And this guy over here, I will not do it again now. When I multiply it with d phi by dx over here, becomes k d phi by dx whole square, minus infinity to plus infinity will vanish. This one over here will become w of phi, which is phi square into 1 minus 2, then phi square into 1 minus 5 the whole square, which is 1 and 0 on the both sides of the interface, that will also vanish. What is left is this fellow, which is h prime of phi, right? Which is now when you multiply with d phi by dx will become just h of phi, and h of phi integrated from minus infinity to plus infinity would be 1 to 0. So if you take the minus sign into account, it will become 0 to 1. Okay. So what you have is h of phi 0 to 1, it is 1 itself. Okay. Okay, so now we described the difference of Fs minus Fl at a given temperature yesterday. What is that? L by Tm. L by Tm. T naught minus Tm. And T naught minus Tm, so we can essentially get a relation between this negative sign, so we become right? No, so this minus and this minus will cancel, so you will still have a minus sign. Okay, this and this will be positive. Okay, this negative sign I'm carrying over to this side. All right. This integral we know how to do. We know how to do this integral, right? How do we do this integral? Okay, I'm going to transform this integral from x to x into phi, right? Which would mean that this is 1 to 0. dt, and what is dt by dx? dt by dx comes from my this equation that we had before, w by k, p to 1 minus t, okay. Minus, remember, so I will have this as v to but remember, dt by dx, we have the condition where it is 1 on the left and 0 on the right. It would mean that I have to choose the negative sign when I take the root over here, right? So the negative of this, which would invert this integral from 1 to 0 to 0. All right? Here. So what is this integral? 1 by 2 plus 1 by 3 to give you by 6. So v root of w 1 by 6. So your relation that you get is following. So equal to minus so we can take this minus inside now. Because this is undercooling, right? So what you get, you can describe your undercooling as Tm to root WK 6 times V. Okay? And if you compare it with this relation, this is your care equation in the sharp interface. Now comes the calamity. What is the calamity? Calamity is, as I said, you have an experimental condition where beta is 0. But in the sharp interface limit, you get a finite beta out of the bottom, which you cannot make 0. You can't make it 0. So where is M, by the way? There is M. We should not forget M. This M was here because of M. So we have forgotten M, which will come here. Okay. So M, for this guy to become 0, W and over K cannot become 0. There is an interface. Tm cannot be 0. So the only way this can become 0 is I have infinite n. Right? I have a value of infinite n. If I have infinite n, I can't do a phase field computation. Right? I can't integrate. So because it's a time dependent problem, I have a finite evolution of this with a finite time scale evolution. Right? So I can't have beta equal to 0. Calamity. So I cannot do a simulation where my interface kinetic coefficient effectively becomes 0. Okay? So this was a calamity. Until someone realized that in reality you are not approaching this limit at all in your simulation. Right? As I said, in reality you are having simulations where you are not at the sharp interface limit, you are actually larger. Right? Your interfaces are finite. Not as small as this, slightly larger than this. And because of this, it provides you an avenue to do something. Okay? And that is just mathematical trickery. But it's essential to know that that is possible. So what we are essentially going to do is that this doesn't allow you to realize experimental conditions. We are essentially therefore going to use a finite interface width and bring some change to our assumptions. Okay. Okay. So what we are going to be doing is the following. We said when the interface is rather narrow, the temperature is rather uniform across the interface, right? Let's say now we make the interface touch, like we have here. Not as large and exaggerated the view. What you are essentially having now is that there's a temperature variation across the interface. So T is no longer constant across the interface. In reality, when you use an interface width which is slightly larger, the temperature will vary across the interface. It's not very constant. Okay? So I'm going to be therefore utilizing that concept for my. So to first find out, if I were to think about this variation, how to get this variation inside the interface, right? That means how does P of x vary inside the interface? So I need that in the driving force over here, which is not constant anymore. I will have P of x anymore. Alright? So to do that, this is what I will do. I will resort to this equation. Right? This equation will down over here, where I will still assume that dt by dx in this region over here is still much smaller than the rest of the region in the macroscopic diffusion length, right? It's still smaller because this over here is limited by the interface width. So it's the variation that you will have here is of the order of the interface, okay? In comparison to what you have, right? So when I integrate this once, you'll have the situation that you integrate from the left of the interface to the right of the interface. It will be delta t from this point to this point. I'm going to call this as delta t is equal to k dt by dx on the liquid side minus k solid side minus NV. To integrate this once, you get h of t, which will be NV times h of t, which integrates from solid to liquid. It is on the liquid side t is 0, right? So you have 1 minus h of t. On the liquid side 0, so this is minus h of t. Or minus l. So plus l. Alright? On the right hand side it's 0, left hand side is minus. Good. So we said that this delta t that you have over here, which is the variation here, is still going to be much smaller than the LB that we have. Therefore, I'm going to be ignoring this delta t across the face. All the while, I'm still wanting to have the dt by dx. So, this is my variation across the interface. But what I'm also going to be doing now, remember, I don't want just the in this here or this here. I'm also wanting to know how the dt by dx varies inside the interface region. So I have to integrate it in a slightly from in the form that I can get dt by dx out. So to simplify this, I'm going to ignore this as I said, and I'm going to integrate this once. Not all the way to the liquid, but some point in x, so that I can get the value out. Thus, h of t equal to 0. I'm going to ignore this part because I'm saying that this part is rather small. Now, there is one more constraint over here. The dt by dx, remember, as the way I have drawn, this is the temperature over here. I'm going to assume that the temperature in the solid is uniform. Okay, so the dt by dx on the solid side is going to be assumed to be vanishing, which means that h of t minus 1. Correct? So what is the nature of this evolution equation? Think about it. No, the dt by dx is on the solid side 0, of t 1, and on the liquid side, what's the value? Minus LB by K, which is what this slope is. That's a Stefan condition, right? So you recover the Stefan condition at this point, and you have a variation all the way to 0 at this point. Okay, that's your dt by dx in the interface. Is that okay? Now with that, what we are going to be attempting to do is to allow for this deviation while we are trying to get the steady state velocity of the interface. Okay? So we'll write it down again. Remember, T is now no longer uniform in this region. There is a small variation which I want to take into account. Alright? So when I take this integration now, I have to be careful that T is no longer constant. It has to be a function of x. Alright? So I want to simplify this to its original form. Okay? And now I'm going to follow the same way of integrating this to multiply this with dt by dx. Again, assuming that the phi profile that I'm integrating with is very close to the original equilibrium form, so that I can multiply it with the equilibrium. Okay, so I will integrate this, making it dt by dx to square. And again, the same properties hold. When I multiply this, become dt by dx the whole square, integrated from minus infinity to plus infinity. The integration will vanish. This will become w of t squared into 1 minus t the whole square, minus and plus the integration will vanish. And I'm now going to worry about this particular part. This will not be the same as the sharp interface. So let's concentrate on this part. We have integration of minus infinity to infinity, L by dm. Okay. So how do I propose to do the integration? Remember now, this is a function of x. This also is a function of x, right? And I want to still do the integration. Right? How do I go about doing it? I have dt by dx, but not t. Any ideas? Integrate by parts. Good. So I will essentially integrate what and differentiate what? You can integrate this one. Okay. Let's do that. So you have this is essentially dh by dx. So we will return this guy as dh by dx. Okay, dx. So we will integrate this and differentiate this one. So all right, computed at minus infinity and plus infinity, right? Which is what? This will become essentially 1, right? And you have the second part, which is coming from here, this L by Dm dt by dx Is that all right? So what we'll have now is that the dt by dx that we need over here will borrow from the thing that we just derived, which is a function of t, right? So dt by dx is Lb by k h of t minus 1. I'm going to substitute it in this direction. So you have this is 1. Rather, it will become t on the solid side because that is the where h of p is found. T0 minus Cn minus L by Dm times h of p times dt by dx is L by k times v, right? H of p minus 1 dx. Alright? Good. So what did we get? We had a term which is over here, not minus here. And we get a term which is proportional to velocity on this side of the equation. On the left hand side of the equation, what you have? A term also proportional to velocity. Okay? And that will be the fun that we are going to be doing now. So how do we evaluate this? I'll just write down this part of it. Minus v L squared by dm. Okay. And what you have here is h of p times h of p minus 1. And just to make our life easy, we will convert this integral into an integral of p like this, which would imply that dx over dp at p equals this is 1 and this is 0. Right? And dx by dp is something we know from past. So in the interest of time, we will assume that we can compute this integral. Right? We will compute this integral and name it. What do we name this integral? We name this integral as okay, we name this integral m for some reason, and then write down our relation that we have over here. No, m is a bad term. M is bad because m is going to interfere. Because remember, our m is existing from that acceleration. The constant factor m. The minus term sitting over here, so we are going to be having did we take the minus into consideration when we came inside here? Huh? No? Then this has to be this minus came from here, so
minus is big cancel.
huh?
In LHS we have a reduction.
No, what I'm asking is this minus m, this minus m multiplied with the sharp interface limit, what did we get? This negative sign that you have over here, that got finally became a positive value, right? So a negative sign will be there. So I think what should happen is I missed track of that negative sign. So let's the time being have this. This is what must happen, right? So you have minus m L by Tm T naught minus Tm plus L square V. Okay. And we said that integral is not m, we will limit some other thing. What shall we limit as? Huh? What is it? P. Okay. And this m is irritating me, so I will hold it here. Yes. All right. Very good. So this integral we evaluated just now. What is this? It is here, right? So we have Tm by 6m root of w by k, right? Times v. And this one we will go on this side. Minus L square v by Tmk times p. Remember p is the integral. And I take the v out. Because both terms are proportional to v, right? I take both the terms v out. And what we have on the right hand side is L by Tm times minus of T naught minus Tm. So that will become Tm. Right? Rather, this integration was this integration was root of w by k times 1 by 6. Okay, this is your integration. You basically have 1 by 6 root of w by k. This is your classical integration. M is minus L square over Tmk is equal to L by Tm, Tm minus c. Right? And we all have just appreciated that Tm minus T naught is delta T. So I can take this on the other side. L by L. Now you see the fun of this. What is the fun? Instead of delta T being equal to your original estimate, you have delta T is equal to a difference of two terms times velocity. So effectively, this is your beta. Okay? And this beta, remember, this is the interface width. Right? This is the interface width. So you can choose your interface width because this is the integral that you can evaluate. You can choose your interface width in a way that this term becomes 0. Right? Or given the interface, these are not free parameters. K is a material parameter, L is a material parameter, M is a material parameter. The only thing you can actually change is the interface width. Right? So you choose the interface width such that your interface kinetics vanishes. Also, but it essentially is not direct. So, but P is directly into function of P. It is there, but here it will give us finite value. dx over dp will essentially come to, it will be a real number given W and K, but effectively,
Even changing the interface with the minus epsilon to plus epsilon, I can, the limits of x, if I change it to x,
yes,
will change.
yes, but my effective point is, here it is 1 by epsilon, there it will be proportional to epsilon. And thereby, you have a function which can become, can solve for it. Okay? So 1 by epsilon over here, root of K by W, there will come dx by dt will be proportional to epsilon, root of K by W. Right? So you have an estimate, this is fun. In a sharp interface limit, you could not make beta 0. Suddenly, when you allowed for the interface to become a little bit wide, you naturally had to account for the temperature variation in the interface. And if you account for that in the driving force of the equation, you naturally then have an estimate for the undercooling at the interface, which must be dependent on the interface width. Okay? And because the interface width determines the undercooling at the interface, you can choose the interface width in a way such that the undercooling at the interface vanishes. Alright? Giving you beta equal to 0.
The velocity dependent part of that.
There's no velocity dependent. There's only velocity. Velocity is moving. Beta is 0. I want to make beta 0.
Undercooling the system, right?
Undercooling the system is there, but undercooling at the interface.
Okay.
We are talking about delta T at the interface, right? What am I actually worried about? Essentially, if I take this value, that is Tn. Okay, that means T naught minus Tn is 0. Alright, and that is ensured if you choose your epsilon K and W in a way that this term vanishes. Okay, so this is the fantastic idea first proposed by Alan Karma. We opened the world for quantitative physical simulations for materials in 1996. Okay, it's a PRL paper, which got focused. Beautiful. Okay. Beta equal to 0. So beta equal to 0. Good. This is a very important derivation. Can we break for 15 minutes before we go to the anti-trapping current? Any questions on this? All right. The idea is pretty simple. What you did was, instead of making an interface with rather small, over here where the temperature is rather constant, you allow for the interface to be a little bit wide, which is realistically what you will be using anyway for your simulations. Because if you use zero interface width, you can't do simulator. It will be finitely wide anyway. But if you're finitely wide, you naturally have to invoke a connection of the driving force at the interface, right? Which will be such that it will allow you for the correction at the interface of the temperature to be flexible. Right? That's the idea. Very nice idea. It's an insight which is at some level very difficult to imagine, right? But if you do it formally mathematically, it's something that comes out. Good.
Within the interface, the driving force is very.
It's varying. In this assumption, it is varying. It's not constant, no. The temperature is varying. All I have assumed is that this difference is much smaller than L. LB. Okay?
Can you assume another way, like driving force as the assumption is that is constant, that you reform?
That is not a clean derivation. I mean, you could do it, but it's essentially going to involve the same sort of integrals if I imagine it correctly. Because you are going to basically find out the average driving force across the interface and then impose that. But that is effectively what you are doing anyway.
Actually, Peter Boole has done one.
Yeah, but that's the same thing. That's essentially going to be the same thing because what you are going to be assuming is this effective driving force has to be such that you compute the driving force and effectively replace with the average driving force across the and compute that average. That's it. Okay, we'll break for 15 minutes, reconfigure our cells at 10, then continue with the very, very difficult concept of the anti-trapping current. In fact, the most difficult concept of this field.